So at the end of the previous section, I mentioned that we are now finally ready for the classification fine-tuning. However, there is one more thing we have to take care of, and that is the calculation of the classification loss and accuracy. And so we will be using the accuracy to track the progress during training, and the classification loss is used similar to what we have done in chapter 5 for optimizing the model weights. So yeah, in the grand scheme of things, where we are, we prepared the data set, we initialized the model, we loaded the pre-trained weights, and then we modified in the previous section the model for classification fine-tuning. Now this one more thing entails that we implement the evaluation utilities before we can move on to the fine-tuning. So we have to just conceptually explain what is going to happen. So here's a figure that is maybe somewhat familiar to you, because here there are similar elements to a figure that you have seen in chapter 5, except that this is a bit smaller and simpler. So in chapter 5, we explained how we go from the model input to the logits, to the Softmax probabilities, and then to the token IDs. And here what we are looking at is the similar flow. So we have, for example, you won the lottery as text input, which goes into the LLM. And then what we're looking at here is the logits vector of the last row of the logits. So going back to the previous section, we had, for example, 4 tokens as input. This could be a text similar to you won the lottery. And then we are looking at the output logits for each of the 4 token IDs. And what we said is we are going to focus on the last row. So we are going to focus on this row here. And so this is what you are seeing here. So these are the logits corresponding to the last row in the logits tensor. And then we could apply the softmax function to convert this into probabilities. And then in chapter 5, what we did is we looked at the position where we have the highest probability, and that was our predicted token ID. Now, this is exactly the same concept, except that instead of 50,257 dimensions, we only have 2 dimensions. One is not spam and one is spam, or better shown here at the bottom. So index position 0 is not spam, index position 1 is spam. In this case, the highest probability is at the first position, so the model would predict 0, not spam, for this particular input. As you might guess, this is not correct, right? I mean, I'm guessing here, but I would say if you receive a text message that says you won the lottery, it's probably going to be spam. And so the model thinks with 99% probability that this is not spam. That's because the model is not trained yet. We want to train it so that this probability here becomes higher, that this is spam, and then the model outputs a 1, and vice versa for the second input. Do you have time? I would say this is probably not spam. It's maybe a message by a friend asking us if we have time. And then here in this case, the highest probability is at spam, and so the model would output spam. And also, again, our goal is to, shift the prediction more towards not spam, assuming that this is really not spam. Yeah, and so we are going to implement this now in code, where we essentially have the same workflow or a similar workflow that we had in the previous chapter. And then when we have these predictions, these labels, we can compute the accuracy. So the accuracy is a measure that tells us how often the model is correct. So for example, if we have 100, let's say 100 text messages, and the model makes 50 correct predictions, that's a 50% accuracy. It's basically random guessing. We want the model to get a accuracy that is close to 100. That means that it gets almost all the 100 out of 100 messages classified correctly. And so let's first, before we code the accuracy, let's first code what we are seeing here in this figure, this conversion from logits to probabilities to the labels. So let's work with the last row here, like I mentioned before, and that was for the reason of the causal attention mask, as I said before. So let's go ahead and just call that our logits. So in reality, these are the last row logits, right? So it's not the whole logits, it's just the last row here that we get with the -1 here. And then let's compute the probabilities. So we do torch.softmax and logits as input, and -1 because we have 2D tensor. And then let's just look at this. And so we can see this is a very small number, something close to 0, where this is 99% essentially 0.999. So this means basically shifting the dot by one position. So we have 0.99, a very high probability. So if we then used our torch Argmax on Probas, you should see a 1 because this is a much higher value than this one, for example. We can call that our label, for instance, like this. And so this is our predicted label. If we want this as a regular Python integer, we can also use the item method, which will just extract this as an integer. There's one more interesting thing maybe to mention. So we are executing this here on the probas, but as I mentioned before in chapter 5, so when we look at the Logits and the Softmax probabilities, you might notice that the Softmax is a strictly increasing function. So that means when we apply a Softmax function to any vector, the ordering of the magnitudes will be the same. So what I'm trying to say here is if the largest value is at the first position before the softmax, it will also be at the first position after the softmax. So it preserves the position of the largest element essentially that we're looking for. It's preserving the whole order of the values. If you would sort them, the sort order would be the same before and after applying the softmax, which means that so the softmax becomes redundant here. So we can actually just do logits here and you will see it will be the same label. So in a sense, we skip one relatively expensive, I mean, not that expensive, but we skip a computation here, which is nice. So we don't really have to apply this function here. For training, it is necessary. But as you remember, we also pass the logits directly into the cross entropy loss, where the cross entropy loss is internally using softmax essentially. So long story short, when we just care about the label, we don't need the softmax because the relative ordering of the elements is the same. So we can just apply the argmax to the logits and save one computation. So now let's get to implementing the accuracy ladder so that we can see how often our model is correct before we start training it. And then, of course, we want to see that it improves during the training. So let's call that calc accuracy ladder. And so this will be analogous to the calc loss ladder we implemented in chapter 5, except now instead of computing the loss, we compute the accuracy. By the way, we will also implement the calc loss ladder again later, but let's, for simplicity, just focus on the accuracy ladder for now. So we will be able to pass a data ladder that could be the training, validation, or test data set or ladder. Then the model itself, I like to also pass the device here so that we can put the data onto the correct device where the model is. There are different ways to implement this, but I prefer to do it this way. The number of batches. So similar to the calc loss ladder, sometimes we don't need to calculate the loss over the whole data set. So for example, if we just need a quick estimate of the validation set and our validation set is very large, it would be pretty expensive to iterate over the whole validation set. So sometimes it's sufficient to only take 2 batches or 3 batches to estimate the accuracy. So with that, we can control how many batches we want. So it's never a bad idea to put the model into evaluation mode. We might have done this at some earlier point, but just doing it here explicitly to make sure things like dropout and so on are disabled, all the random things in the model. And then we can keep track of the predictions. So the correct predictions, I'm just seeing I made a typo here, the correct predictions and the number of predictions in total that will be used later to calculate the accuracy. And then we can have just like a little sanity check. So if the number of batches is none, then let's just use the whole data set. So here we will do the length of the data ladder. So that means use all the data points in the data set. Yeah, so far so good. Then let's say otherwise. We take the num batches, but let's make a small modification. So we say num batches, the minimum value between this and also the length in the data loader. So this will prevent issues where, for example, our data set only has 2 batches, but we specified 10, and then it would crash or something like that. So here we say whatever number is smaller. So if we define 10, but our data loader only has 2, then we only use 2. It's just like a little safeguard here. And then we say for I, let's say input batch, target batch in the data loader, enumerate, data loader. So here, for each of them, we will say if the number is smaller than num batches, we keep working on this, right? So if I is smaller than the batches, then we will first transfer the data onto the target device. So to device and target batch also to device. So yeah, right now I'm just double checking. I just want to make sure 1, 2, 3, 4, everything looks correct. Yeah, usually I don't code in a Jupyter notebook. I usually use Visual Studio Code with torch.nograd. Let's maybe make a computer logits. So here logits equals to model, and then the input batch where we have it here. And like I said before, we will only use the last row. And then we convert this to predicted labels, and this will be using our computation here. Since we have similar, I think it doesn't hurt just to add the -1 here, similar to what we have done here. I think it's not strictly necessary, but not a bad idea. Forgot a T here. What else? So now we have the predicted labels, and so we can increment the number of, let's say, call this examples, the number of examples we have encountered so far. Num examples plus equals, and then the number of rows here, the shape 0, should contain the number of examples. So this is just, we could also get that from the input batch. It's the same, it's the number of rows or number of elements in that case. What else? So now, of course, the important part would be the correct predictions. So here, simplest way how we can say if we have some correct predictions is just to compare it to the target batch. So for example, if I have a torch tensor, let's say labels 1, 2, 3, or we have, let's say just 0, 1, 0, 1. And this is our, let's say, correct, or let's call that target. And then we have predictions. Let's take this one and change one number here. And so if I compare those two, I can use the equal sign, and it will give me a Boolean array where true means it's similar and false means it's not similar. So maybe just lining them up here, then it's a bit more clear. So we are lining them up here. And so what I can do is I can then use the sum to calculate how many of them are correct. So in this case, this should give me a 4 because I have 4 correct predictions, and I can return this as an item, for example. And what I can do is I can say target.shape 0. This should give me 1, 2, 3, 4, 5 divided by, let's do it like this, sorry, 4 divided by 5. And this gives me essentially the accuracy if our data set only consists of 5 examples. So here, this gives me 0.8 or 80% prediction accuracy. 4 or 5 are calculated or predicted correctly. And so we can use that to compute the accuracy here, we can say the number of correct predictions is equal, so sorry, the accuracy is equal to the number of correct predictions, similar to what we have here, divided by the total number, which we kept track of here. So this is the number of correct predictions divided by the number of examples or total predictions. I'm just double checking if everything looks correct. I would say this needs to be indented because we do this for each case where this is true. If this is not true, then we want to, of course, exit. So I think this should work. I'm pretty sure I made a typo, but we will see in a few moments. So let me also define, because we're going to need it here, the device. So the device, I usually like to do torch device and then CUDA. If torch.CUDA is available. And otherwise we will use the CPU. And yeah, like I mentioned in chapter 5, you might also want to use just the MPS device, but again, numbers might slightly differ if you use the MPS device. And then let's put the model to the device, and let's just use a random seed. Should not be necessary because we are completely, or if we are completely iterating over the data set, we don't need a random seed. But if we want to, for example, only do it for 10 batches, how many, by the way, do we have? Let me double check. We had somewhere checked the length of the data set. It's been a while here. So if we only want to take 10 batches just to accelerate this a bit, if we have shuffling in the training set, it will of course give us a different 10 batches. So in that case, we are setting a random seed so that you should hopefully get the same accuracy that I'm getting. So let's say train accuracy, and then we initialize our calculate accuracy loader on the training set, train loader, the model, device, and then let's say num batches, let's say 10. So in this case, this hopefully gives us the training accuracy. So let's see if this works or whether I made a typo here somewhere. Yes, so there is something that is not working. Correct prediction. So I think this should be correct predictions. And this is, it seems to be working. So let's see what the calculation gives us. Okay, so I forgot one more thing. I should have, of course, applied the sum item here. Looks better, or I hope it works. Okay, so 0.46. So this is our accuracy. So this is essentially 46.25%. And we can do the same thing also for the validation accuracy. Well, loader, and then the test accuracy. So 45%, and then the test accuracy, 48%. So they should be all very close together. However, note that we are estimating the accuracy of the training set by only sampling 10 out of the 130 batches. So if you want to get the exact training accuracy, you can do, num batches none. But yeah, this is just like a rough estimate to estimate how accurate the model is. And you can see it's roughly, 50%. It's kind of like guessing here because it has not been trained. So it's just guessing whether input example is 0 or 1. And if you are just guessing and you have a 50% chance being correct or incorrect, it should roughly be 50%. And so this is what we have here for the accuracy loader. Now let's take care of the loss loader, because that is also what we need to optimize the model. So for that, let me go back to chapter 5. So we had the dev calc loss loader somewhere here, loss batch and loss loader. Let me copy just this one for now. So here we have the loss loader, and notice we make one modification. Of course, we do the last row only instead of everything. And then I can actually get rid of the flatten. We don't need to flatten anything anymore. And this should be my loss loader. And then we can use also the same, the loss batch. We can use the same loss loader. Notice we can't really import this technically from the previous chapter because this one is now different, right? So this we have changed this slightly. So if you just import this from the previous chapters file, you might get unexpected results because your calc loss loader would be using the calc loss batch from that file, which is slightly different. Maybe it's not even in here. Okay, so it's also maybe better that it's not in here, that I haven't copied it in here. But yeah, so I recommend just defining it separately here and here for this particular chapter. Yeah, okay, so this hopefully works. And then we can use it similar to what we have done before. So we can calculate the training set loss. Like this, and then I can also do the same while it's calculating for the validation and test set. And these are our initial values. So what we want is we want to reduce this to 0. And we want to increase this number so it becomes 1, so 100% accuracy. So yeah, so this is so far what we have set up in terms of how we evaluate our model. And then in the next video, like I promised earlier, we will be finally fine-tuning this model.
Get this book at Manning.com.